This presentation is delivered by the Stanford Center for Professional Development.
Okay. So, welcome back. What I want to do today is start a new chapter in 229, and in particular, I want to talk about learning theory. So in the previous, I guess, 8 lectures so far, you've learned about a lot of learning algorithms, and you actually now, I hope, understand and know about, some of the best and most powerful tools of machine learning and of AI. And all of you are now sort of well qualified to go into industry and build powerful learning algorithms that apply really the most powerful learning algorithms we know to all sorts of problems. And in fact, I hope you start to do that on your projects right away as well. But you might remember, I think it was at the very first lecture that I made an analogy to if you're trying to learn to be a carpenter, right? So if you imagine you're going to carpentry school to learn to be a carpenter, then only a small part of what you need to do is to acquire a set of tools, right? So if you learn to become a carpenter, you don't walk in and pick up a toolbox and graduate. So when you need to cut a piece of wood, do you use a rip saw or a jigsaw or a keyhole saw or whatever? It's really mastering the tools that's also an essential part of becoming a good carpenter. And what I want to do in the next few lectures is actually give you a sense of the mastery of the machine learning tools that all of you have. Okay? And so in particular, in the next 3 lectures, what I want to do is to talk more deeply about the properties of different machine learning algorithms so that you can get a sense of when it's most appropriate to use each one. And it turns out that one of the most common scenarios of machine learning is someday you'll be doing research or starting a company, and you apply one of the learning algorithms you learned about. You may apply logistic regression or support vector machines or naive Bayes or something. And for whatever bizarre reason, it won't work as well as you were hoping. It won't quite do what you were hoping it to. And so to me, what really separates the people that really understand and really get machine learning, compared to people that maybe read a textbook and sort of work for their math, will be what you do next. It will be in your decisions of when you apply a support vector machine and it doesn't quite do what you wanted. Do you really understand enough about support vector machines to know what to do next and how to modify the algorithm? And to me, that's often what really separates the great people in machine learning versus the people that read a textbook and sort of saw the math and sort of just understood that. Okay. So what I want to do today, today's lecture will mainly be on learning theory, and we'll start to talk about some of the theoretical results of machine learning. The next lecture later this week will be on algorithms for sort of explicitly addressing or fixing some of the problems that the learning theory will point out to us and help us understand. And then 2 lectures from now, that lecture will be almost entirely focused on the practical advice for how to apply learning algorithms. Okay? So, any questions about this before I start? Okay. So the very first thing I want to talk about is something that I've probably already seen on the first homework, and something that I alluded to previously, which is the bias-variance trade-off. Right? So take ordinary least squares, the first learning algorithm we learned about. If you fit a straight line to this data, this is not a very good model, right? And if this happens, we say it has underfit the data. We say that this is a learning algorithm with very high bias because it's failing to fit the evident quadratic structure in the data, right? And for the purposes of this cartoon, you can informally think of the bias of a learning algorithm as representing the fact that even if you had an infinite amount of training data, even if you had tons of training data, this algorithm would still fail to fit the quadratic function, the quadratic structure in the data. And so we think of this as a learning algorithm with high bias. then there's the opposite problem. Right, so that's the same data set. If you fit a four-folded polynomial to this data set, then you'll be able to interpolate the 5 data points exactly. But clearly, this is also not a great model to the structure that you and I probably see in the data. Right? And we say that this algorithm has a problem, is overfitting the data. Or alternatively, that this algorithm has high variance. Okay, and the intuition behind overfitting or high variance is that the algorithm is fitting spurious patterns in the data, or is fitting idiosyncratic properties of this specific data set, be it the data set of housing prices or whatever. Right? And quite often, there'll be some happy medium of fitting a quadratic function that maybe won't interpolate your data points perfectly, but also captures more of the structure in your data than a simple model which underfits. I should say that you can sort of have exactly the same picture for classification problems as well. So let's say this is my training set. Right, of positive and negative examples. And so, and so you can fit logistic regression with a very high order polynomial to this, right? So h of theta of x equals the sigmoid function of, whatever, sigmoid function applied to a 10th order polynomial. And if you do that, maybe you get a decision boundary like this. Right, that does indeed perfectly separate the positive and negative classes, but this is another example of overfitting. And in contrast, if you fit logistic regression to this model with just the linear features, with none of the quadratic features, then maybe you get a decision boundary like that, which can also underfit. Okay. So what I want to do now is understand this problem of overfitting versus underfitting, of high bias versus high variance, more explicitly. And we'll do that by posing a more formal model of machine learning and sort of trying to prove when these two twin problems, when each of these two problems come up. And as a motivating example, for our initial foray into learning theory, I want to talk about linear classification, in which h of x is equal to g of theta transpose x. Okay, so the linear classifier. And for this class, I'm going to use I'm going to use g as indicator z greater than or 0. Okay. So with apologies in advance for changing the notation yet again, for the support vector machine lectures, we use y equals -1 or +1. For the learning theory lectures, it turns out it'll be a bit cleaner if I switch back to y equals 0 or 1 again. So I'm going to switch back to my original notation. And so you can think of this model as a model for as logistic regression, say. You can think of this as being similar to logistic regression, except that now we're going to force the logistic regression algorithm to output labels that are either 0 or 1. Okay, so you can think of this as a classifier that outputs labels 0 or 1 rather than probabilities. And so, as usual, let's say we're given a training set of m examples. Oops. Right, that's just my notation for writing a set of m examples ranging from I equals 1 through m. And I'm going to assume that the training examples xi, yi are drawn iid from some distribution script d. Okay, iid stands for identically independently distributed. And if you're running a classification problem on houses, like features of a house, comma, whether the house will be sold in the next 6 months, then this is just the probability distribution over features of houses and whether or not they'll be sold. Okay, so I'm going to assume that training examples will draw an IID from some probability distribution script D. Well, same thing for spam. If you're trying to build a spam classifier, then this would be the distribution of what emails look like, comma, whether they are spam or not. Right? And in particular, to understand to understand the phenomena of bias and variance, I'm actually going to use a simplified model of machine learning. And in particular, logistic regression fits its parameters to model like this by maximizing the log likelihood. But in order to understand learning algorithms more deeply, I'm actually going to assume a simplified model of machine learning. And let me just write that down. So I'm going to define training error as, so this is a training error of a hypothesis h subscript theta. So write this epsilon hat of h subscript theta. If I want to make the dependence on the training set explicit, I write this with a subscript s there, where s is the training set. And I'll define this as let's see. Okay, I hope the notation is clear. This is a sum of indicated functions for whether your hypothesis correctly classifies the ith example. And so when you divide by m, this is just in your training set, what's the fraction of training examples your hypothesis classifies. So define that as a training error. And training error is also called risk. And the simplified model of machine learning I'm going to talk about is called empirical risk minimization. And in particular, I'm going to assume that the way my learning algorithm works is it will choose parameters theta that minimize my training error. Okay? And it will be this learning algorithm that will prove properties about. And it turns out that, you can think of this as the most basic learning algorithm, right? The algorithm that minimizes your training error. Turns out that logistic regression and support vector machines can be formally viewed as approximations to these. So turns out that if you actually want to do this, this is a non-convex optimization problem. It actually turns out to be NP hard to solve this optimization problem. Logistic regression and support vector machines can both be viewed as approximations to this non-convex optimization problem by finding a convex approximation to it. Okay, but think of this as similar to what algorithms like logistic regression are doing. So let me take that definition of empirical risk minimization and actually just rewrite it in a different equivalent way. For the results I want to prove today, it turns out that it will be useful to think of our learning algorithm as not choosing a set of parameters, but as choosing a function. So let me say what I mean by that. Let me define the hypothesis class, script h, as the class of all hypotheses. In other words, as a class of all linear classifiers that your learning algorithm is choosing from. Okay, so right, h subscript theta is a specific linear classifier, and so h subscript theta, right, each of these functions, each of these is a function mapping from the input domain x to the class 0, 1. Each of these is a function, and as you vary the parameters theta, you get different functions. And so let me define the hypothesis class script h to be the class of all functions that, say, logistic regression can choose from. Okay? And so this is a class of all linear classifiers. And so I'm going to define or maybe redefine empirical risk minimization as, instead of writing it as choosing a set of parameters, I want to think of it as choosing a function in the hypothesis class script H that minimizes my training error. Okay. So, actually, can you raise your hand if it makes sense to you why this is equivalent to the previous formulation? Okay, cool. Thanks. So for our development, it would be useful to think of algorithms as choosing from a function from a class instead, because in the more general case, this set stripped H can be some other class of functions. Maybe it's a class of all functions represented by a neural network, or a class of all some other class of functions the learning algorithm wants to choose from, and this definition for empirical risk minimization will still apply. Okay. So, what we'd like to do is understand whether empirical risk minimization is a reasonable algorithm. Alex?
Is each theta still a function that's defined by g of theta dx, or is it now more general?
I see. Oh, right. So let's see. I guess the question is, is h theta still defined by g of theta transpose x, or is this more general? So, yeah. So probably two answers to that. One is this framework is general. So for the purpose of this lecture, it may be useful to you to keep in mind a motivating example of when H subscript theta is a class of all linear classifiers, such as those used by like the perceptron algorithm or logistic regression. Everything on this board, however, is actually more general. H can be any set of functions mapping from the input domain to the set of class labels 0 and 1. And then you can perform empirical risk minimization over any hypothesis class. For the purposes of today's lecture, I am going to restrict myself to talking about binary classification, but it turns out everything I say generalizes to regression and other problems as well. Am I answering your question? Okay, cool. All right. So I want to understand if empirical risk minimization is a reasonable algorithm, and in particular, what are the things we improve about it. So clearly, we don't actually care about training error. We don't really care about making accurate predictions on a training set, or at least that's not the ultimate goal. Right? Our ultimate goal is how well it makes predictions on examples that we haven't seen before. Right? How well it predicts prices or sell or no sale outcomes of houses you haven't seen before. So what we really care about is generalization error, which I write as epsilon of h. And this is defined as the probability that if I sample a new example, x comma y, from that distribution scripts D, my hypothesis mislabels that example. Okay, and in terms of notational convention, usually if I place a hat on top of something, it usually means, not always, but it usually means there's an attempt to estimate something without a hat, right? So, for example, epsilon hat here, this is something that we're trying to think of epsilon hat training error as an attempt to approximate generalization error. Okay, so the notation convention is usually the things with a hat on top are things we're using to estimate other quantities. And h hat is a hypothesis output by a learning algorithm to try to estimate what the function is from x to y. So let's actually prove some things about when empirical risk minimization will do well in the sense of giving us low generalization error, which is what we really care about. In order to prove our first learning theory result, I'm going to have to state two lemmas. The first is the union bound. which is the following. Let's A1 through AK be K events. And when I say events, I mean events in the sense of a probabilistic event that either happens or not. And these are not necessarily independent. Okay. So there's some joint distribution over the events A1 through AK, and maybe they're independent, maybe not. No assumption on that. Then the probability of A1 or A2 or dot to dot up to AK, right? This this union symbol, this hat, this just means this sort of just set notation for probability just means or, right? So the probability of at least one of these events occurring of A1 or A2 or up to AK, this is less than or equal to the probability of A1 plus probability of A2 plus dot 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 plus probability of AK. Okay. So the intuition behind this is just that, I'm not sure if you've seen Venn diagrams depictions of probability before. If you haven't, what I'm about to do may be a little cryptic, so just ignore that. Just ignore what I'm about to do if you haven't seen it before. But if you have seen it before, then this is really, this is really, right, the probability of A1 union A2 union A3 is less than to P of A1 plus P of A2 plus P of A3, right? So that the total mass in the union of these three things is less than or equal to the sum of the masses in the three individual sets. It's not terribly surprising. It turns out that depending on how you define your axioms of probability, this is actually one of the axioms of probability theory. So I won't actually try to prove this. This is usually written as an axiom. So sigma sub additivity of probability measures is what it's sometimes called as well. But in learning theory, it's commonly called the union bound, so I just call it that. The other lemma I need is called the Hoeffding inequality. Again, I won't actually prove this. I'll just state it, which is let's let Z1 up to Zm be M IID Bernoulli random variables with mean phi. So the probability of Zi equals 1 is equal to phi. So let's say you observe M IID Bernoulli random variables and you want to estimate their mean. So let me define phi hat, and this is again that notation, no convention. Right? Phi hat means is our attempt to is our estimator or something else. So let me define phi hat to be 1 over m sum from I equals 1 through m Zi. Okay, so it's just our attempt to estimate the mean of these Bernoulli random variables by sort of taking its average. And let any gamma be fixed. Then the Hoeffding inequality is that the probability your estimate of phi is more than gamma away from the true value of phi, that this is bounded by 2e to the negative 2 gamma squared m. Okay? So just in pictures, so this theorem holds, this lemma, the Hoeffding inequality, this is just a statement of fact. This just holds true. But let me now draw a cartoon to describe some of the intuition behind this, I guess. So let's say the x-axis is a real number line from 0 to 1. And so phi is the mean of your Bernoulli random variables. You will remember from, whatever, some undergraduate probability or statistics class the central limit theorem that says that when you average a lot of things together, you tend to get a Gaussian distribution, right? And so when you toss m coins with bias phi, when you observe these m Bernoulli random variables, and then you average them, then the probability distribution of phi hat right will roughly be a Gaussian, let's say. Right? And it turns out, if you haven't seen the result before, it's actually that the cumulative distribution function of phi hat will converge to that of a Gaussian. Technically, phi hat can only take on a discrete set of values because these are fractions 1 over m. So it doesn't really have a density, but just as a cartoon, think of it as it'll converge roughly to a Gaussian. So what the Hoeffding inequality says is that if you pick a value gamma, that's one interval gamma, that's another interval gamma, then it's saying that the probability mass out in the tails, in other words, the probability that my value of phi hat is more than gamma away from the true value, that the total mass, that the total probability mass in these tails is at most 2 e to the negative 2 gamma squared m. Okay, that's what the Hoeffding inequality. So if you can't read that, this just says this is just the right hand side of the bound, 2 e to the negative 2 gamma squared m. So it bounds the probability that you make a mistake in estimating the mean of a Bernoulli random variable. And the cool thing about this bound, the interesting thing behind this bound is that it decreases exponentially in m. Right? So it says that for a fixed value of gamma, as you increase the size of your training set, as you toss the coin more and more, then the width of this Gaussian will shrink. Right? The width of this Gaussian will actually shrink like 1 over root m. And that would cause the probably mass left in the tails to decrease exponentially quickly as a value as a function of m. Right? And this will be important later. Yeah.
Does this come from the inequality?
No, it doesn't. So this is proved. This is proved by different. This is no. So the central limit theorem. There are many versions of the central limit theorem, but the versions I'm familiar with are sort of asymptotic. But this works for any finite value of m. Oh, in particular, this bound holds even if m is equal to 2 or m is equal to 3, right? So if m is very small, the central limit theorem approximation is not good at all. But this theorem holds regardless. Okay, but I'm drawing this just as a cartoon to help explain the intuition, but this theorem just holds true, without reference to central limit theorem. Okay. All right. So let's start to understand empirical risk minimization. And what I want to do is begin with studying empirical risk minimization for a slightly simpler case than, say, logistic regression. And in particular, I want to start with studying the case of finite hypothesis classes. So let's say script H is a class of k hypotheses right? So this is k functions with no, each of these is just a function mapping from inputs to outputs. There are sort of no parameters in this. And so what the empirical risk minimization would do is it would take the training set and it will then look at each of these k functions and it will pick whichever of these functions has the lowest training error. Okay? So an algorithm like logistic regression uses an infinitely large, continuous infinitely large class of hypotheses, script H. But to prove the first result, I just want to just describe our first learning theory result for the case of when you have a finite hypothesis class, and then we'll later generalize that to infinite hypothesis classes. So empirical risk minimization picks the hypothesis of the lowest training error. And what I'd like to do is prove a bound on the generalization error of h hat. All right. So prove that somehow minimizing training error also allows me to do well on generalization error. And here's the strategy. I'm going to, the first step in this proof, I'm going to show that training error is a good approximation to generalization error. And then I'm going to show that this implies a bound on the generalization error of the hypothesis output by empirical risk minimization. Okay. And I just realized this class, I guess, is also maybe slightly notation heavy class where I'm sort of just introducing, a reasonably large set of new symbols. So if, again, in the course of today's lecture, you're looking at some symbol and you don't quite remember what it is, please raise your hand and ask. Raise your hand and ask, what is that? Was that generalization error or was it something else? So raise your hand and ask if you don't remember some of the notation I was defining. Okay, so we're going to do this in 2 steps. And in particular strategy is I'm going to show training error is a good approximation to generalization error. And this will imply that minimizing training error will also do pretty well in terms of minimizing generalization error. And this will give us a bound on the generalization error of the hypothesis output by empirical risk minimization. Okay. So here's the idea. So let's even not consider all the hypotheses at once. Let's pick any hypothesis hj in the class script h. And so until further notice, let's just consider one fixed hypothesis. So pick any one hypothesis and let's talk about that one. Let me define zi to be indicator function for whether this hypothesis misclassifies the ith example, that is z subscript I. Okay? So, right. So zi will be 0 or 1, depending on whether this one hypothesis, which is the only one I'm going to even consider now, whether this hypothesis misclassifies the example. Right? And so, my training set is drawn randomly from some distribution script D, right? And depending on what training examples I got, these zi's will be either 0 or 1. So let's figure out what the probability distribution over zi is, right? Well, so zi, takes on the value either 0 or 1. So clearly it's a Bernoulli random variable. So you can only take on these values. And right. Well, what's the probability that zi is equal to 1? In other words, what's the probability that that from a fixed hypothesis hj, when I sampled my training set IID from distribution D, what was the chance that my hypothesis will misclassify it? Well, so by definition, that's just the generalization error of my hypothesis hj, right? So zi is a Bernoulli random variable with mean given by the generalization error of this hypothesis. Raise your hand if that made sense. Oh, cool, great. And moreover, all the zi's have the same probability of being 1, and all my training examples I draw in IID, and so the zi's are also independently of and therefore, the zi's themselves are IID random variables. Okay, because my training examples were drawn independently of each other by assumption. So, if you revisit the definition of training error, the training error of my hypothesis Hj, that's just that, right? That's just the average of my zi's, which was, well, I previously defined it like this. Okay. And so epsilon hat of Hj is exactly the average of m IID Bernoulli random variables drawn from a Bernoulli distribution with mean given by the generalization error, right? So this is well, this is the average of m IID Bernoulli random variables, each of which has mean given by, you know, the generalization error of Hj. And therefore, by the Hoeffding inequality, we have that the probability that the difference between training and generalization error, probably this is greater than gamma, is less than equal to 2 e to the negative 2 gamma squared m. Okay? Exactly by the Hoeffding inequality. And what this proves is that for my fixed hypothesis Hj, my training error epsilon hat will, with high probability, so if assuming m is large, if m is large, then this thing on the right-hand side will be small, because it's 2 e to the negative 2 gamma squared m. So this says that if my training set is, you know, large enough, then the probability my training error is far from generalization error, meaning that it's more than gamma, will be small, will be bounded by this thing on the right-hand side. Okay? Now, here's the slightly tricky part. What we've done is to prove this bound for one fixed hypothesis for Hj. What I want to prove is that training error will be a good estimate for generalization error, not just for this one hypothesis Hj, but actually for all k hypotheses in my hypothesis class script H. So let's do, well, let's do the new board. So in order to show that, let me define a random event. Let me define Aj to be the event that let me define Aj to be the event that, you know, the difference between training and generalization error is more than gamma on a hypothesis Hj. And so what we proved, you know, on the previous board was that the probability of Aj is less than or equal to 2 e to the negative 2 gamma squared m, and thus it's pretty small. Now, what I want to bound is the probability that there exists some hypothesis in my class script H such that I make a large error in my estimate of generalization error, okay, such that this holds true. So this is really just, right, the probability that there exists a hypothesis for which this holds. This is really the probability that, you know, A1 or A2 or up to AK holds, right? This is, so the chance that there exists a hypothesis is just, well, the probability that, you know, for hypothesis 1, I make a large error in estimating the generalization error, or for hypothesis 2, I make a large error in estimating generalization error, and so on. And so by the union bound, this is less than or equal to that which is therefore less than equal to equal to which is equal to that. Okay. So let me just take 1 minus both sides. So of the equation on the previous board, let me take 1 minus both sides. So the probability that there does not exist a hypothesis such that the probability that there does not exist a hypothesis on which I make a large error in this estimate, well, this is equal to the probability that for all hypotheses I make a small error, or at most gamma, in my estimate of generalization error. And then taking 1 minus of the right-hand side, I get 2k e to the negative 2 gamma squared m. Okay? And so, and the sign of the inequality flipped because I took 1 minus both sides. The minus sign flips the sign of the inequality. So what we've shown is that with probability, which I abbreviate to WP, with probability 1 minus 2k e to the negative 2 gamma squared m, we have that epsilon hat of h will be within gamma of epsilon of h. Oops. Simultaneously for all hypotheses in class script h. And so, just to give this name just to give this result a name, this is called. This is one instance of what's called a uniform convergence result, and the term uniform convergence, this sort of alludes to the fact that this shows that as m becomes large, then these epsilon hats will all simultaneously converge to epsilon of h. That training error will become very close to generalization error simultaneously for all hypotheses h. That's what the term uniform refers to, is the fact that this converges for all hypotheses h and not just for one hypothesis. And so what we've shown is one example of a uniform convergence result. Okay. So let me clean a couple more boards, and I'll come back and ask what questions you have about this. We should take another look at this and make sure it all makes sense. What questions do you have about this?
How is the value of gamma computed? The threshold.
Right. Yeah. So let's see. Questions: how's the value of gamma computed? So for the purposes of this, gamma is a constant. So imagine that gamma is some constant that we chose in advance, and this is a bound that holds true for sort of any fixed value of gamma. Later on, as we take this bound and sort of develop this result further, we'll choose specific values of gamma to plug into this bound. For now, let's just imagine that we'll prove this holds true for any value of gamma. Any questions? Yeah.
The hypothesis space is infinite, obviously small.
Yes. So what happens in the hypothesis space is infinite. So this simple result won't work in its present form, but we'll generalize this. I probably won't get to it today, but we'll generalize this at the beginning of the next lecture to infinite hypothesis clauses.
How do we use this theory in practice?
Oh, how to use theory in practice. So let me, I might get to a little of that later today. We'll talk concretely about algorithms, the consequences of the understanding these things in the next lecture as well. Yeah, okay, cool. Can you just raise your hand if the things I've proved so far make sense? Okay, cool, great. Thanks. All right, let me just take this uniform convergence bound and rewrite it in a couple of other forms. So this is sort of a bound on probability. This is saying, suppose I fix my training set M and fix my training set, fix my threshold, my error threshold gamma. What is the probability that uniform convergence holds? Right? And well, that's my formula that gives the answer. This is the probability of something happening. So there are actually three parameters of interest. One is what is this probability? The other parameter is what's the training set size M, and the third parameter is what is the value of this error threshold gamma. I'm not going to vary k for these purposes. But so there are two other equivalent forms of the bound, so you can ask, given gamma, and so what we proved was given gamma and given m, what is the probability of uniform convergence? The other equivalent forms are, so given gamma and the probability delta of making a large error, how large a training set size do you need in order to give a bound on how large a training set size do you need to give a uniform convergence bound with parameters gamma and delta? And so so if you set delta to be equal to 2k e to the negative 2 gamma squared m, this is that formula I had on the left. And if you solve for m, what you find is that there's an equivalent form of this result that says that so long as your training set size m is greater than this, and this is the formula that I get by solving for m. Okay, so long as m is greater than or equal to this, then with probability, which I'm abbreviating to WP again, with probability at least 1 minus delta, we have for all. Okay, so this says how large a training set size do I need to guarantee that with probability at least 1 minus delta, we have that training error is within gamma of generalization error for all my hypotheses, and this gives an answer. And just to give this another name, this is an example of a sample complexity function. Right? So from undergrad computer science classes, you may have heard of computational complexity, which is how much computation do you need to achieve something. So sample complexity just means how large a training example, how large a training set, how large a sample of examples do you need in order to achieve a certain bound and error. And it turns out that in many of the theorems we write out, you can pose them in sort of the form of a probability bound or a sample complexity bound or in some other form. I personally often find the sample complexity bounds the most easy to interpret because it says how large a training set do you need to give a certain bound on the errors. And in fact, well, we'll see this later. Sample complexity bounds often sort of help to give guidance for really if you're trying to achieve something on a machine learning problem. This really is trying to give guidance on how much training data you need to prove something. the one thing I want to note here is that m grows like the log of k, right? So the log of k grows extremely slowly as a function of k. The log is one of the slowest growing functions, right? It's one of, well, some of you may have heard this, right? That for all values of k, right? I learned this from a colleague, Andrew Moore, at Carnegie Mellon. But you know, in computer science, for all practical purposes, for all values of k, log k is less than equal to 30. Right? This is almost true. So logs is one of the slowest growing functions, and so the fact that m, the sample complexity, grows like the log of k, means that you can increase the number of hypotheses in your hypothesis class quite a lot, and the number of training examples you need won't grow very much. Okay, right. Let's not keep that there. Okay. Right. But this property will be important later when we talk about infinite hypothesis classes. The final form is the, I guess, what's sometimes called the error bound, which is when you hold m and delta fixed and solve for gamma. Okay, and so well. And what you do, what you get then is that with probability at least 1 minus delta, we have that for all hypotheses in my hypothesis class, the difference in training and generalization error will be less than or equal to that. Okay, and that's just solving for gamma and plugging the value I get in there. Okay. All right. So So the second step of the overall proof I want to execute is the following. Right, the results I've been showing are essentially that uniform convergence will hold true with high probability. What I want to show now is, let's assume that uniform convergence holds. So let's assume that for all hypotheses H, we have that epsilon of H minus epsilon hat of H is less than or equal to gamma. Okay. What I want to do now is use this to see what we can prove about the bound of see what we can prove about the generalization error. Right. So I want to know, can we suppose this holds true? I want to know, can we prove something about the generalization error of H hat, where again H hat, right, was the hypothesis selected by empirical risk minimization. Okay. So in order to show this, let me make one more definition. Let me define H star to be the hypothesis in my class script H that has the smallest generalization error. So this is, you know, if I had an infinite amount of training data, or if really I could go in and find the best possible hypothesis in the sense of minimizing generalization error, what's the hypothesis I would get? Okay, so in some sense, it sort of makes sense to compare the performance of our learning algorithm to the performance of H star, because we clearly can't hope to do better than H star. Another way of saying that is that a hypothesis class is a class of all linear decision boundaries, but the data just can't be separated by any linear function. So if even H star is really bad, then there's sort of is unlikely. Then there's just not much hope that your learning algorithm could do even better than H star, right? So I actually proved this result in 3 steps. So the generalization error of H hat, the hypothesis I chose, this is going to be less than or equal to that. Actually, let me number these equations. Right? This is because of equation 1, because I assume that epsilon of H hat and epsilon hat of H hat were within gamma of each other. Now, because H star, now by the definition of empirical risk minimization, right? H hat was chosen to minimize training error, and so there can't be any hypothesis with lower training error than H hat. So the training error of H hat must be less than or equal to the training error of H star. Right? So this is by 2, by the definition of H hat as the hypothesis that minimizes training error H hat. And the final step is going to apply this uniform convergence result again. We know that epsilon hat of H star must be within gamma of epsilon of H star. And so this is at most plus gamma. And then I have my original gamma there. Okay, and so this is by equation 1 again because, because I know the training error of H star must be within gamma of the generalization error of H star. And so, well, I'll just write this as plus 2 gamma. Okay. Yeah.
Notation is epsilon parentheses H hat. That's not the training error. That's the generalization error with some estimate of the hypothesis.
Oh, okay. Let me just let me write that down on this board. So actually, let me think. Can I fit that? Okay, no, maybe I'll fit this in here. So epsilon hat of H is the training error of a hypothesis H. In other words, given a hypothesis is just a function, right? Mapped from X to Y's. So epsilon hat of H is, given a hypothesis H, what's the fraction of training examples it misclassifies? And generalization error of H is, given a hypothesis H, if I sample another example from my distribution script D, what's the probability that H will misclassify that example? Does that make sense? Oh, okay. And H hat is the hypothesis that's chosen by empirical risk minimization. When I talk about empirical risk minimization is the algorithm that minimizes training error, and so epsilon hat of H is the training error of H. And so H hat is defined as the hypothesis that, out of all hypotheses in my class script H, the one that minimizes training error H, epsilon hat of H. Okay. All right. Yeah.
So, H star should be a member of capital H, the hypothesis family, right?
Yes, it is.
So what happens if the generalization of H star is something here?
I'll talk about that later. Yeah. So let me tie all these things together into a theorem. Let there be a hypothesis clause given with a finite set of k hypotheses. And let any m delta be fixed. then, so I fixed m and delta, so this will be the error-bound form of the theorem, right? Then, with probability at least 1 minus delta, we have that the generalization error of h hat is less than or equal to the minimum overall hypotheses in set h epsilon of h plus 2 times plus that. Okay? So to prove this, well, this term, of course, is just epsilon of h star, right? And so to prove this, we set gamma to equal to that. This is 2 times the square root term. Right? To prove this theorem, we set gamma to equal to that square root term. Say that again? Wait, say that again? Oh, yes, thank you. Right. That didn't make sense at all. Thanks. Thanks, right. So set gamma to that square root term. And so, you know, we know equation 1, right, from the previous board, holds with probability 1 minus delta, right? Equation 1 was the uniform convergence result, right? That, well, i.e. this was equation 1 from the previous board, right? So set gamma equal to this, we know that with probabilities 1 minus delta, this uniform convergence holds. And whenever that holds, that implies, you know, I guess if we call this equation star, I guess. And whenever uniform convergence holds, we showed, again on the previous board, that this result holds. That generalization error of h hat is less equal to generalization error of h star plus 2 times gamma. Okay, and so that proves this theorem. So this result sort of helps us to quantify a little bit that bias variance trade-off that I talked about at the beginning of, actually near the very start of this lecture, right? And in particular, let's say I have some hypothesis class script h, right, that I'm using. Maybe it's a class of all, you know, linear functions in linear regression, or logistic regression with just the linear features. And let's say I'm considering switching to some new class h prime by adding more features. So let's say this is linear and this is quadratic, right? So the class of all linear functions is a subset of the class of all quadratic functions, and so h is a subset of h prime. And let's say I'm considering, you know, instead of using my linear hypothesis class, let's say I'm considering switching to a quadratic hypothesis class. So switching to a larger hypothesis class. Then what are the trade-offs involved, right? Well, I proved this only for finite hypothesis classes, but we'll see this if something very similar holds for infinite hypothesis classes too. But the trade-off is, well, if I switch from h to h prime, if I switch from linear to quadratic functions, then epsilon of h star will become better, right? Because you know, the best hypothesis in my hypothesis class will become better. Right? The best quadratic function, by best I mean in the sense of generalization error, right? The hypothesis function with the quadratic function with the lowest generalization error has to have, you know, equal or more likely lower generalization error than the best linear function. So by switching to a more complex hypothesis class, you can get this first term to go down. But what I pay for then is that k will increase. Right? By switching to a large hypothesis class, the first term would go down, but the second term would increase because I now have a larger class of hypotheses, and so the second term, k, will increase. Right? And so this is sometimes called the bias. This is usually called the bias variance trade-off, whereby going to large hypothesis class, maybe I have the hope of finding a better function, but my risk of sort of not fitting my model so accurately also increases, and that's because shown by illustrated by the second term going up when the size of your hypothesis class, when k goes up. And so, speaking very loosely, when think of this first term as corresponding maybe to the bias of the learning algorithm, or the bias of my hypothesis class, and you can, again, speaking very loosely, think of the second term as corresponding to the variance in your hypothesis. In other words, how well you can actually fit a hypothesis in the, how well you actually fit, fit this hypothesis class to your data. And by switching to more complex hypothesis class, your variance increases and your bias decreases. Okay. This is another warning. It turns out that if you take like a statistics class, you've seen definitions of bias and variance, which are often defined in terms of squared error or something. It turns out that for classification problems, there actually is no universally formal, there's no universally accepted formal definition of bias and variance for classification problems. For regression problems, there is, so the square error definition. For classification problems, it turns out, there have been several competing proposals for definitions of bias and variance. So when I say bias and variance here, think of these as very loose, informal, intuitive definitions and not formal definitions. Okay. So the cartoon associated with the intuition I just said will be as follows. Let's say, and everything I'm about to plot will be for a fixed value of m, right? For a fixed training set size m. Vertical axis I'll plot error, and on the horizontal axis I'll plot model complexity. And by model complexity, I mean, sort of degree of polynomial, size of your hypothesis class script h, etc. Okay, it actually turns out, you remember the bandwidth parameter from locally weighted linear regression. That also has a similar effect to controlling how complex your model is. So by model complexity, you think of it as degree of polynomial, I guess. So the more complex your model, the better your training error. And so, training error will tend towards 0 as you increase the complexity of your model, because the more complicated your model, the better you can fit your training set. But because of this bias variance trade-off, you find that generalization error will come down for a while and then it'll go back up. And this regime on the left is when you're underfitting the data, or when you have high bias. And this regime on the right is when you have high variance, or you're overfitting the data. Okay, and this is why a model of sort of intermediate complexity, somewhere here, is often preferable to since our goal is to minimize generalization error. Okay, so that's just a cartoon. In the next lecture, we'll actually talk about the number of algorithms for trying to automatically select model complexity, say, to get you as close as possible to this minimum, to this area of minimized generalization error. So the last thing I want to do is I should go back to this. Is actually going back to the theorem I wrote out. I just want to take that theorem. Well, so the theorem I wrote out was an error-bound theorem, right? This says for fixed m and delta, with probably 1 minus delta, I get a bound on gamma, which is what this term is. So the very last thing I want to do today is just come back to this theorem and write out a corollary where I'm going to fix gamma, I'm going to fix my error bound and fix delta and solve for m. And if you do that, you get the following corollary. Let H be fixed with k hypotheses, and let any delta and gamma be fixed. Then, in order to guarantee that let's say I want to guarantee that the generalization error of the hypothesis I choose with empirical risk minimization, that this is at most 2 times gamma worse than the best possible error that I can attain with this hypothesis clause. Let's say I want this to hold true with probability at least 1 minus delta. Then it suffices that m is greater than or equal to that. Okay, and this is solving for the error bound for m. One thing you might go and convince yourself, so the easy part of this is if you set that term equal to gamma and solve for m, you will get this. One thing I'll actually go home and sort of convince yourselves of is that this result really holds true, right? That this really logically follows from the theorem we've proved. In other words, you can take that formula you wrote, solve for m, and this is the formula you get for m. That's the easy part. But once you go back and convince yourselves that this theorem is a true fact and that it does indeed logically follow from the other one. And in particular, make sure that if you solve for that, you really get m greater than or equal to this. And why is this m greater than or equal to that and not m less than or equal to? And just make sure I can write this down and it sounds plausible. Once you just go back and convince yourself that it's really true. Okay. It turns out that when we prove these bounds in learning theory, it turns out that very often the constants are sort of loose. So it turns out that when we prove these bounds, usually we're interested in, usually we're not very interested in the constants. And so I write this as big O of 1 over gamma squared log k over delta. And again, the key step in this is that the dependence on m with the size of the hypothesis clause is logarithmic. And this will be important. This will be very important later when we talk about infinite hypothesis clauses. Okay. Any questions about this? Okay, cool. So next lecture we'll come back. We'll actually start from this result again. Remember this. I'll write this down as the first thing I do in the next lecture. And we'll generalize these to infinite hypothesis clauses and then talk about practical algorithms for model selection. So I'll see you guys in a couple of days.